The universe is expanding faster than it should be, and no one knows why. We can only account for a tiny fraction of the energy needed to drive this cosmic acceleration, leaving a staggering 95% of the cosmos unaccounted for. This is the mystery of the universe's missing energy, the greatest puzzle in all of modern physics. Together, we will journey through 30 of the most compelling theories scientists have proposed to solve it. By the end, you will understand the leading contenders in the race to explain the fundamental nature of reality itself. Could the answer lie in ghostly fields, hidden dimensions, or a fundamental flaw in our laws of physics? What do you believe is the most likely explanation for the void in our cosmos? Our story begins not with a discovery, but with a mistake. Albert Einstein, in crafting his theory of general relativity, believed the universe was static and unchanging. His equations, however, insisted that the cosmos should either be collapsing under its own gravity or flying apart. To force his math to match this static view, he introduced a fudge factor, a repulsive force he called the cosmological constant. He later renounced it as his greatest blunder, yet decades after his death, this very idea was resurrected to explain the universe's accelerating expansion. The cosmological constant is now the leading candidate for dark energy. It proposes that empty space is not truly empty. Instead, the vacuum of space itself possesses a constant, unchanging energy density. Think of it as an invisible, ethereal force field woven into the very fabric of the cosmos. This energy exerts a negative pressure, a gentle but relentless push against the pull of gravity. As the universe expands and more space comes into existence, the total amount of this vacuum energy increases. This is the key. Unlike matter, which dilutes and weakens as the universe grows, the energy density of the cosmological constant remains the same everywhere forever. Imagine blowing up a balloon with tiny dots painted on it, representing galaxies. Now, imagine the rubber of the balloon itself has a built-in, innate tendency to push outward. As you inflate it, the dots move apart, not because they are moving on their own, but because the fabric between them is actively stretching, driven by this inherent energy. That is the cosmological constant at work. It is an elegant solution fitting the data beautifully, but it introduces a profound new mystery. The calculated energy density of this vacuum energy is astronomically, almost impossibly, smaller than what quantum field theory predicts it should be. We are off by a factor of 1 followed by 120 zeros. This is arguably the worst theoretical prediction in the entire history of science. So while the cosmological constant elegantly describes what we see, its origin remains one of the deepest enigmas in physics. But what if Einstein's constant is not so constant after all? This leads us to a second, equally fascinating theory known as quintessence. Imagine the cosmological constant as a perfectly steady, unwavering hum from the vacuum of space. Quintessence, by contrast, is more like a cosmic melody that changes its tune over billions of years. It proposes that dark energy is not a fixed property of empty space, but a dynamic, evolving force field that permeates the entire universe. Scientists often call it a fifth fundamental force, something entirely separate from gravity, electromagnetism, and the nuclear forces. Unlike the stubborn cosmological constant, the energy density of quintessence can change over time, growing stronger or weaker as the universe ages. Think of it not as a permanent feature of the cosmos, but as a kind of cosmic fuel. In one popular version of this idea, this fuel is slowly, gradually running out. This offers a potential solution to a subtle mystery in the data. The acceleration of the universe might not be perfectly constant. Perhaps it was stronger in the distant past, or maybe it is weakening now. Quintessence can account for this. If this energy field is decaying, its repulsive push would diminish over cosmic time. It is as if the universe had a powerful burst of acceleration in its youth, but is now gradually coasting. The allure of quintessence is its flexibility, its ability to tell a more complex story about the evolution of the cosmos. Yet this very flexibility is also its greatest weakness. Because it can be tuned to fit many possible futures, it is much harder to pin down with observations. Is the cosmic engine still roaring, or is it quietly winding down? The answer remains hidden in the deepening cosmic night. Perhaps the entire problem stems from a single, flawed assumption. What if our most trusted law, the one that guides spacecraft and describes the fall of an apple, is fundamentally incomplete? This is the radical proposition of modified Newtonian dynamics, or MOND. It dares to suggest that Isaac Newton's famous law of universal gravitation, later refined by Einstein, is not the final word. Instead of inventing an invisible, undetectable form of matter to explain cosmic behavior, MOND proposes we simply rewrite the rules of gravity itself on the grandest scales. The core motivation for this idea comes from the perplexing behavior of galaxies. When astronomers observe the speed at which stars orbit the center of a galaxy, they find something bizarre. According to Newton's laws, stars on the outer edges, feeling less gravitational pull, should move much more slowly than those near the center. Yet observation after observation reveals that these distant stars orbit just as fast, as if the galaxy contains far more mass than we can see. This is the classic evidence for dark matter, but MOND offers a different solution. It introduces a tiny modification to the force of gravity when that force becomes incredibly weak, which happens naturally in the sparse outer regions of galaxies. It is not that there is extra mass yanking on those stars, but that gravity itself behaves differently when its pull is exceptionally faint. Imagine you are pushing a heavy box across a normal floor. It requires a certain amount of force to get it moving. Now imagine that same box on a surface of ice. With the same push, it accelerates much more easily because the friction is different. MOND suggests that the fabric of space-time itself has a different kind of friction, or rather a different set of rules, when gravitational accelerations drop below a certain, almost imperceptible threshold. This single tweak to the equations makes the predicted rotation of galaxies match what we actually see, all without a single particle of dark matter. If MOND is correct, then a huge portion of the universe's missing mass and the energy budget problem tied to it simply vanishes. We have been trying to find invisible stuff to fix our equations when the equations themselves were the problem all along. This is a profoundly elegant idea, but it faces its own immense challenges, forcing us to question everything we think we know about the fundamental forces that shape our reality. Yet the idea of rewriting gravity still leaves us with the accelerating expansion of the universe, the domain of dark energy. To tackle that, we must venture into a far more speculative and mind-bending realm. Our cosmos may not be the entire story. What if our universe is merely one bubble in an infinite cosmic foam, a single page in a book with endless chapters? This is the multiverse hypothesis, and it offers a startling explanation for the missing energy. In this view, the fabric of reality is a vast landscape of universes, each with its own unique physical laws and constants. Some might be stillborn, collapsing instantly. Others could be sterile, without any matter. Our universe, with its just right conditions for life, is one lucky bubble among countless others. But these universes are not entirely isolated. Through the strange laws of quantum mechanics, energy could be slowly trickling out of our cosmos and into a neighboring one. Picture our universe as a sturdy but aging wooden boat floating on a calm, endless sea. For years, the boat has remained afloat, seemingly solid and self-contained. Yet slowly, imperceptibly, it begins to sit lower in the water. You can find no hole, no single point of failure, but the water level inside is undeniably rising. The boat is leaking, not from a dramatic gash, but from a million tiny, invisible seams where the planks of wood meet. In the multiverse model, these seams are quantum tunnels or vibrations in the fabric of spacetime itself, known as brains in some string theory concepts. Energy, the very force that drives our cosmic expansion, could be seeping through these microscopic passages into the greater multiverse outside. We would not see this energy leave, just as you cannot see the air slowly escaping from a slightly porous balloon. We only measure the consequence, a universe that seems to be losing its driving force, an acceleration that appears weaker than our theories predict. The energy is not gone, it has simply flowed into a reality we cannot perceive. This solves the cosmological constant problem in a novel way, suggesting the vacuum energy we measure is not a true constant but a slowly decaying value as our universe bleeds into the void. The profound implication is that the fate of our entire cosmos might be tied to realities we can never touch, leaving us to wonder if we are truly alone or merely one voice in an infinite, silent chorus. Even our universe's slow leak into the multiverse might be a gentle fate compared to the sheer violence of another possibility. Phantom energy is a form of dark energy so potent and so bizarre that its equation of state, a simple number describing its pressure and density, is less than -1. This small mathematical deviation from the cosmological constant unlocks a future of absolute cosmic destruction. If dark energy is phantom energy, then the acceleration we observe today is not just a constant push, it is a force that grows stronger over time. The repulsive power of this energy field would increase as the universe expands, creating a terrifying feedback loop. More expansion leads to stronger dark energy, which leads to faster expansion, on and on until the very fabric of reality is overwhelmed. This is the theoretical endgame known as the Big Rip. Imagine the universe's expansion starting as a gentle tide, but slowly transforming into a raging tsunami that nothing can withstand. Billions of years from now, long before the rip itself, the acceleration would become so fierce that it would first tear the universe apart on the largest scales. Galaxy clusters bound by gravity would be the first to be shredded. The immense gravitational glue holding thousands of galaxies together would be no match for the phantom force. Next, individual galaxies like our own Milky Way would be pulled apart. Stars would be flung into the ever-emptying void, their planetary systems scattered into darkness. But the destruction would not stop there. In the final moments, the phantom energy's grip would tighten. The very stars and planets themselves would be torn asunder. The forces holding a star together, the immense gravity battling the nuclear fires within, would be overcome. Every star would explode in a silent, cosmic flash. Then, in the last fraction of a second, the scale would become personal and atomic. The phantom force would grow so strong that it would exceed the very forces that bind molecules, then atoms, and finally even atomic nuclei together. Every piece of matter in the universe would be violently dissociated into a thin, expanding cloud of fundamental particles, unable to ever interact again. Space-time itself, the stage upon which the cosmos plays out, would be shredded beyond recognition. This scenario has a profound implication for the universe's missing energy. If dark energy is phantom energy, then the total energy content of the vacuum is not just constant. It is effectively infinite, growing without bound as it fuels its own catastrophic acceleration. The mystery of the missing energy transforms into a terrifying question of overabundance, a force so powerful it ultimately consumes everything it was meant to drive. The sheer violence of phantom energy forces us to question the very stage upon which the cosmos is built. What if the three-dimensional reality we experience with its galaxies, stars, and planets is not the fundamental truth? We may be living in a cosmic illusion, a hologram. This is not science fiction, but a serious theoretical framework born from the study of black holes and string theory. The holographic principle suggests that our universe, in all its vast three-dimensional glory, is actually a projection of information encoded on a distant, two-dimensional surface that forms its outer boundary. Think of a common credit card hologram, a flat sticker that creates a stunning, three-dimensional image when you tilt it. Now, imagine that on a cosmic scale. The entire universe, every atom, every force, every event within the volume of space, could be nothing more than a complex projection from a flat, two-dimensional shell at the edge of everything. This bizarre idea emerged from a startling discovery about black holes. The amount of information a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon, the point of no return. This implies that all the information about what falls into a black hole is somehow painted onto its two-dimensional surface. The holographic principle boldly applies this logic to the entire cosmos. If this is true, it completely redefines our concepts of energy, space, and information. The energy we perceive and measure in our three-dimensional world would be a derived property, a consequence of the information processing happening on that distant two-dimensional boundary. The mystery of the universe's missing energy could then be a colossal accounting error. We are trying to balance the books by counting the properties of the three-dimensional projection, while the real ledger, the true source of all energy and information, exists on a two-dimensional surface we cannot see. Our perception of a vacuum filled with a certain energy density might be an illusion, a translation effect from a more fundamental reality where the rules are completely different. The energy is not missing, we are simply reading the shadow instead of the object casting it. This theory challenges the core of our experience, suggesting that the solidity of the world is a magnificent and profound deception, and that the answer to our greatest cosmic puzzle might be written on the walls of the universe itself. Sometimes the most profound transformations are the ones we cannot see directly. A seventh theory suggests our universe is not just expanding, but fundamentally changing state, like a cosmic version of water freezing into ice. This idea is called vacuum metamorphosis. It proposes that the accelerating expansion of the universe is not caused by a mysterious new substance, but is instead a symptom of the vacuum of space itself undergoing a dramatic phase transition. We see phase transitions all around us. When liquid water cools to its freezing point, it doesn't just get colder, it reorganizes into a completely new structure with different properties, becoming solid ice. Vacuum metamorphosis argues that something similar is happening to the fabric of reality on a grand scale. As the universe expands and the density of matter and radiation drops below a certain critical threshold, the vacuum of space is triggered to shift into a new, more stable state. This new vacuum state possesses a different and much lower energy density. Think of it like a cosmic pressure release valve. For most of cosmic history, the universe was dense and hot, filled with radiation and matter, which kept the vacuum locked in a high-energy state. But as expansion diluted everything, the vacuum finally reached its tipping point and crystallized into its true, lower-energy form. This sudden drop in vacuum energy density is what we are measuring as dark energy. It is not a new force pushing the universe apart, but the aftermath of the vacuum settling into its final configuration, a change that itself drives further acceleration. The acceleration is both the trigger and the result, a self-perpetuating cycle born from a fundamental shift in the nature of emptiness. This theory is elegant because it requires no new, undetectable particles or fields. The explanation lies in the properties of the vacuum we already inhabit, suggesting that the answer to our greatest cosmic mystery was hidden in plain sight all along, waiting for the universe to cool enough to reveal its true face. What if the two greatest mysteries of the cosmos are actually one and the same? An eighth theory proposes a radical simplification, suggesting that dark matter and dark energy are not separate entities at all, but different manifestations of a single, exotic substance known as Chaplygin gas. This concept unifies the cosmic inventory, replacing two profound unknowns with one. Picture a strange cosmic fluid that can change its fundamental character over billions of years. In the dense, crowded universe of the past, this fluid would have clumped together under gravity, behaving exactly like the invisible scaffolding of dark matter that guides the formation of galaxies. It would have provided the gravitational tug needed to gather clouds of gas and dust into the first stars and galaxies. But as the universe expanded and grew more diffuse, this same substance would have undergone a dramatic transformation. Its internal pressure would change, causing it to stop clumping and instead begin to push, driving the galaxies apart in an accelerating expansion. In this late phase of cosmic history, it would behave precisely like dark energy. Think of water, which can be a solid, shaping the landscape as ice, and then later a vapor, expanding to fill any container. Chaplain gas is a theoretical fluid with an equally dramatic but far more exotic phase shift. Its equation of state, the mathematical rule linking its pressure and density, allows it to be stiff and attractive when the universe is dense and repulsive when it is empty. This single component could solve two colossal puzzles at once, offering an elegantly simple cosmic ledger. The appeal is undeniable, a beautiful economy of explanation. Yet, this unified model faces significant challenges. The way this gas must clump to form the dark matter structures we see does not perfectly match all astronomical observations. It is a compelling, all-encompassing idea, but one that requires the universe to play by a very specific and strange set of rules, leaving us to wonder if the cosmos truly favors such an elegant simplicity, or if its deepest secrets are destined to remain separate and distinct. The origin of everything might hold the key to this modern enigma. Our ninth theory rewinds the cosmic clock all the way back to the first moment, the Big Bang itself. It dares to ask a heretical question. What if the energy is not missing at all? What if the universe was simply born this way, with a specific, lopsided set of initial conditions that make it appear from our current vantage point to be running on empty? This idea suggests the deficit is not a flaw in our physics, but a feature of our particular cosmic inheritance. One compelling line of thought involves the universe's profound matter-antimatter asymmetry. In the fiery forge of the Big Bang, energy should have condensed into equal amounts of matter and its mirror opposite, antimatter. When these two meet, they annihilate in a flash of pure energy. Yet, for every billion pairs that destroyed each other, a single particle of matter somehow survived. That tiny, 1 in a billion imbalance is why we have a universe filled with galaxies, stars, and planets, instead of a featureless sea of radiation. But what if that initial lottery was even more specific? Perhaps the process that favored matter over antimatter also imprinted a unique signature on the geometry and energy budget of the cosmos. The universe may have been born with a slight gravitational debt or a specific curvature that preordained its current state of accelerated expansion. Think of it like inheriting a unique family heirloom, a watch that always runs a little fast. You might spend your life trying to fix it, adjusting the gears, convinced it is broken. But the watch is not broken. It was simply crafted to keep its own peculiar time. From our perspective inside the cosmos, the watch appears to be gaining seconds, and we invent complex explanations for its strange ticking. But from the perspective of its creation, it is performing exactly as intended. The apparent acceleration and missing energy are not driven by a mysterious new force, but are the long-term, inevitable consequence of how the universe was wound up at the beginning of time. This reframes our entire search. We are not hunting for a lost component of the cosmos, but are instead deciphering the faded blueprint from its birth, a single, elegant line of code written 14 billion years ago that determined everything that was to follow. Our most trusted constant might not be so constant after all. The speed of light is a cornerstone of modern physics, a universal speed limit etched into the fabric of reality. But what if this fundamental number has changed over the life of the cosmos? This is the startling proposal of the time-varying speed of light theory. It suggests that in the universe's first fleeting moments, light traveled at a rate vastly faster than it does today. This single, radical change could untangle some of cosmology's most stubborn knots. Consider the horizon problem. The cosmic microwave background, the ancient afterglow of the Big Bang, shows a nearly uniform temperature across the entire sky. Yet, regions on opposite sides of the universe have not had enough time, traveling at the speed of light, to exchange heat and reach this equilibrium. It is as if two people in separate, soundproof rooms spontaneously began humming the same precise tune without ever having communicated. If the speed of light was once immeasurably higher, however, those distant regions could have been in causal contact, easily evening out their temperature before the light speed dropped to its current value. Then there is the flatness problem. Our universe appears incredibly flat on large scales, meaning its geometry adheres perfectly to the rules of Euclidean geometry. For this to be true after billions of years of expansion, the initial conditions at the Big Bang had to be fine-tuned to an astonishing degree of precision, like balancing a pencil on its tip for eternity. A faster speed of light in the early universe alters the equations governing its expansion, naturally driving it toward this flat state without requiring any miraculous fine-tuning. How does this connect to the missing energy? The total energy density of the universe is directly linked to its geometry and expansion history. By allowing the speed of light to vary, we are effectively rewriting the story of that expansion. The apparent deficits and imbalances we measure today, the very things we label dark matter and dark energy, could be illusions created by our mistaken assumption that the speed of light has always been the same. We are trying to measure a cosmic journey using a ruler that has subtly changed length, and our calculations are coming up short because of it. This theory forces us to question the most basic tools in our scientific toolkit, suggesting that the answer to our cosmic mystery may require us to abandon one of our most cherished constants. Our understanding of gravity may be built on a fundamental illusion. Eric Verland has proposed a radical new vision where gravity is not a fundamental force of nature, but something that emerges from a much deeper concept, the flow of information and the tendency of systems to become disordered, a property known as entropy. In this entropic gravity framework, the force we feel as gravity is a side effect, a statistical mirage arising from the way information is stored and processed on the cosmic horizon. Think of a movie projected on a screen. You see the actors moving, the story unfolding, the illusion of depth and force. But all of that complex dynamic action is actually encoded in the flat, two-dimensional pixels of the screen itself. Verland suggests our three-dimensional reality works the same way. The gravitational pull of a galaxy, the orbit of a star, these are not the result of a fundamental force described by Einstein, but are the emergent consequence of information changing on a distant, holographic surface that bounds our universe. This single shift in perspective has a stunning consequence. It naturally accounts for the very phenomena we invented dark matter to explain. When astronomers see stars orbiting a galaxy too fast, they infer the presence of invisible matter. But in Verland's emergent gravity, there is no need for dark matter particles. Instead, the extra gravitational influence comes from an interaction between the visible matter of the galaxy and the background entropy of the universe itself. Imagine you're wading through a calm, shallow sea. Your movement is easy, predictable. Now, imagine that sea is filled with an invisible, complex network of shifting currents. As you try to walk, you feel an extra pull and push on your legs, altering your path and speed, even though you cannot see the source. In emergent gravity, the ordinary matter of a galaxy is wading through the entropic fabric of space. In the dense central regions, this effect is minimal, but in the sparse outer reaches, the entropic influence becomes dominant, providing an extra apparent pull that makes the outer stars orbit faster, exactly as we observe, all without any dark matter. This theory goes even further, suggesting that the accelerated expansion of the universe, our dark energy, might also be a manifestation of this cosmic entropy. As the universe expands, the amount of information on its boundary increases, and this changing information content could be the true source of the repulsive push we measure. The universe's missing energy is not missing at all. We have simply been misinterpreting the ledger, trying to account for a force that is not fundamental, while the true cosmic accounting is happening on the holographic walls of reality, where information, entropy, and energy are fundamentally intertwined. This staggering mismatch between prediction and reality is the cosmological constant problem, and it is arguably the most severe failure of theoretical physics. Our two most successful theories, quantum mechanics and general relativity, offer violently conflicting answers to a simple question: how much energy does empty space contain? Quantum field theory calculates the vacuum should be seething with a colossal energy density, a value so immense it would have torn the universe apart in its first instant. Yet our astronomical observations show the actual vacuum energy is almost zero, a whisper so faint we can barely detect its gravitational effect. The difference between these two numbers is a 1 with 120 zeros after it, a number so vast it defies any human analogy. Such a discrepancy is not just a small error, it is a screaming alarm that something fundamental in our understanding is profoundly wrong. This leads to the puzzle of fine-tuning. For the universe to be hospitable to life, the cosmological constant had to be set to an almost impossibly precise value. If it were even slightly larger, that repulsive push would have prevented matter from ever clumping into galaxies and stars. If it were slightly more negative, the universe would have collapsed back on itself long before life could arise. We exist in a razor-thin window of possibility, a cosmic balancing act of unbelievable precision. One proposed solution is the anthropic principle, which suggests that there may be a vast multiverse containing every possible value of the cosmological constant. We, of course, can only find ourselves in one of the rare universes where the value is fine-tuned for our existence. In this view, there is no deeper reason for the number. It is simply a prerequisite for us being here to ask the question. Other physicists seek a more satisfying answer, a cancellation mechanism within the laws of physics itself. Perhaps there is a hidden symmetry or a new particle we have not yet discovered that perfectly offsets the vacuum energy, leaving behind the tiny, residual value we measure. The search for this cosmic counterbalance is one of the most urgent quests in fundamental physics, a hunt for the missing piece that could finally explain why our universe is so quiet, so stable, and so perfectly poised on the edge of nothing. Our reality might be a fragile island in a far vaster cosmic ocean. Brain cosmology, a concept born from string theory, suggests that the three-dimensional space we know and love is just a single slice of a much grander reality. In this view, our entire universe is a three-dimensional membrane or a three-brain, adrift within a higher dimensional space known as the bulk. We are stuck to this brain, unable to perceive the full expanse of the bulk, just as characters drawn on a sheet of paper cannot look up and see the third dimension. This radical shift in perspective offers two breathtaking solutions to the mystery of missing energy. The first involves gravity, the one fundamental force that has always felt curiously weak. Why is the gravitational pull of the entire Earth so easily overcome by a small magnet? Brain cosmology proposes that gravity is not inherently feeble, it is simply diluted. While all other forces, like electromagnetism, are confined to our brain, gravity, the curvature of spacetime itself, can leak out. It spreads into the extra dimensions of the bulk, its strength thinning out across a volume we cannot see. From our limited perspective, stranded on our three-brain, gravity appears weak. This leakage could account for the effects we attribute to dark matter, or it could alter the expansion history of the cosmos in a way that mimics dark energy, all because the true strength of gravity is escaping our notice. The second possibility is even more dramatic. What if the missing energy is not leaking out but flooding in from a collision with a neighboring reality? Our brain may not be alone in the bulk. Parallel universes, other three-dimensional membranes, could be floating nearby. If one of these brains were to collide or simply pass close to ours, the interaction could transfer a colossal amount of energy into our cosmos. Imagine two enormous, soapy films floating on the surface of a pond. As they drift, they might gently touch, ripple, and merge, transferring energy between them. A brain collision would be an event of unimaginable scale, injecting a surge of energy that could kickstart a new phase of cosmic inflation or drive the accelerated expansion we measure today. In this higher dimensional framework, the missing energy is not missing at all. It is a visitor from a reality just beyond our perception, a temporary gift or a permanent scar from a long-ago encounter with another universe. The true nature of our cosmos might be written not just in the stars, but in the hidden geometry of dimensions we have yet to comprehend. Even the emptiest void in the cosmos is not truly empty. At the tiniest imaginable scales, space is a seething, bubbling cauldron of activity known as quantum foam. Here, the principle of quantum uncertainty reigns supreme, and empty space is anything but quiet. Particle and antiparticle pairs spontaneously blink into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing back into nothingness. This endless, frantic dance of creation and destruction is a fundamental property of the quantum world. The energy of these vacuum fluctuations is colossal, and when we try to calculate their total contribution to the cosmos, we get that infamous number, the one with 120 zeros, a value that would have ripped the universe apart. Yet, when we look out at the cosmos, we see a universe that is remarkably stable and smooth. This is the core of the puzzle. Perhaps our method of accounting is fundamentally flawed. The key may lie not in the individual fluctuations, but in their collective behavior over the vast expanse of the cosmos. Think of the quantum vacuum as a perfectly calm sea viewed from a great height. From that perspective, the ocean appears flat and serene. But if you were to drop down to the surface, you would see that it is actually a chaotic mess of individual waves, peaks, and troughs, all crashing into one another. The quantum world is that chaotic surface, while the smooth, large-scale universe we observe is the view from high above. The incredible energy of each tiny fluctuation might be cancelled out when averaged over the immense volume of space, leaving behind only a tiny, residual net energy that drives the gentle acceleration we measure. Another possibility is that we are misunderstanding how these fluctuations interact with gravity. According to general relativity, all forms of energy curve spacetime and produce gravity. But what if the relationship between the quantum vacuum and gravity is more subtle? Some theories suggest that the constant flickering of virtual particles creates a subtle, persistent pressure that counteracts the attractive pull of gravity on cosmic scales. It is as if the fabric of spacetime itself has a built-in springiness, a natural tendency to resist being compressed, and this inherent pressure manifests as the repulsive force we call dark energy. In this view, the missing energy is not missing at all. It has been here all along, woven into the restless, vibrant fabric of nothingness itself. The answer to our greatest cosmic mystery might not require a new substance, but a deeper understanding of the noisy, energetic void that underlies everything we see. This staggering fine-tuning leads us to a 15th theory that reframes the entire mystery. The anthropic principle suggests the universe's missing energy is not a puzzle to be solved, but a prerequisite for our own existence. We are not observing a cosmos with a curiously low energy density by chance. Instead, we could only ever arise in a cosmos that possesses exactly this property. The value of dark energy appears exquisitely balanced, but perhaps that balance is an illusion of our perspective. If the cosmological constant were significantly larger, the universe would have expanded so rapidly that matter could never coalesce into the first galaxies, stars, and planets. There would be no heavy elements, no rocky worlds, and certainly no one to ponder the cosmos. If the value were more negative, the universe would have collapsed in a catastrophic big crunch long before life had a chance to emerge. Our existence itself is proof that we inhabit a universe within a very narrow window of possibility. This is where the concept merges with the multiverse. Imagine an endless cosmic archipelago where each island universe has its own randomly assigned physical constants. In most of these universes, the dark energy density is far too high or too low. They are stillborn or empty or fleeting, but in a tiny, tiny fraction of them, the number falls within the golden range that permits complexity and life. We do not live in a special universe, we live in a viable one. The energy is not missing, it is simply set to a level that allows us to be here to notice it. This is a profound shift in thinking. We are not decoding a cosmic equation to find a unique answer. We are merely reading the name tag on our own habitable room in an infinite hotel of uninhabitable ones. The mystery dissolves from a why into a where. Why is the energy density so low? Because we are here. The search for a deeper physical mechanism may be futile, as the answer is written not in the laws of physics, but in the simple, undeniable fact of our own observation. Perhaps Einstein's masterpiece, the theory of general relativity, is not the final word on gravity. What if we could rewrite it not by adding dark energy, but by adjusting the equation itself? This is the promise of F of R gravity, a class of theories where the R stands for the Ricci scalar, a mathematical measure of how severely spacetime is curved by the presence of matter and energy. In Einstein's original theory, this curvature term is directly proportional to the energy content of the universe. It is a beautifully simple, linear relationship. But F of R gravity proposes that this relationship is not so straightforward on the grandest scales. It suggests that gravity behaves differently when the curvature of spacetime becomes incredibly weak across vast cosmic distances. Think of it like a spring. For small stretches, a spring obeys a simple, linear law. The more you pull, the more it resists. But if you stretch it to its absolute limits near its breaking point, the relationship changes. The spring might stiffen or soften in a way the simple law does not predict. F of R gravity applies this same logic to the fabric of spacetime itself. As the universe expands and the average density of matter drops, the overall curvature of the cosmos becomes incredibly faint. In this low curvature environment, the gravitational force may enter a new regime where its fundamental law is modified. The mathematics of these theories introduce extra terms that act like a built-in cosmic accelerator. When you solve the modified equations for an expanding universe, you find a repulsive component emerges naturally, not from a new substance, but from the altered geometry of gravity itself. The observed acceleration is not driven by dark energy, but is a direct consequence of gravity's own rules changing in an almost empty cosmos. This is not a minor tweak, it is a fundamental shift in our understanding of the dominant force shaping the universe. The appeal is that it uses the geometry we already have to solve the mystery, offering a more economical explanation. Yet these theories face their own rigorous tests. They must not only reproduce the cosmic acceleration, but also perfectly match the intricate details of how galaxies cluster and how light bends around massive objects. The challenge is to bend the rules of gravity just enough to explain the universe's great expansion, without breaking the beautiful, precise predictions that have made Einstein's theory so successful for a century. We are left to wonder if the universe's greatest secret is not a hidden energy, but a subtle correction to the most famous equation ever written. The quiet hum of empty space is not just a theoretical concept, it has a physical push and pull we can measure in a laboratory. This is the Casimir effect, a small but profound force that makes the quantum vacuum real. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in an absolute vacuum, separated by a gap smaller than the width of a human hair. Classically, nothing should happen, but in the quantum world, this tiny gap becomes a cosmic filter. The space outside the plates allows for quantum fluctuations of all wavelengths, a chaotic sea of virtual particles popping in and out of existence. The narrow gap between the plates, however, is so small that it only permits fluctuations with wavelengths smaller than the gap itself. The longer wavelengths are excluded. With more activity happening outside the plates than between them, a net pressure pushes the plates together. They are literally squeezed by the restless energy of the vacuum. This measurable force is a direct signature of zero-point energy, the idea that empty space possesses a fundamental, irreducible energy that never switches off. For decades, a tantalizing hope existed that this omnipresent zero-point energy could be the very engine of dark energy. If the vacuum is truly seething with this intrinsic power, could its sheer abundance be the repulsive force driving the galaxies apart? The heartbreaking reality, however, is a problem of scale. The zero-point energy we calculate from quantum field theory is unimaginably vast, while the dark energy we observe is almost zero by comparison. To power the cosmic acceleration, the energy density of the vacuum must be around 120 orders of magnitude smaller than what the theory predicts for zero-point energy. It is the difference between the energy of a single atom and the energy of the entire observable universe. This is not a small discrepancy to be tweaked, it is a chasm that defies understanding. The Casimir effect confirms the vacuum has energy, but it also highlights the colossal failure of our theories to account for its true strength, or rather, its surprising weakness. The search for dark energy has thus moved from harnessing this quantum background to understanding why it is so eerily silent, leaving us to wonder if the answer lies not in the energy itself, but in a mysterious, perfect cancellation that renders the bustling quantum world almost still on the grandest of stages. Some particles are born to break the rules. Tachyons are purely hypothetical entities that defy our most fundamental law of physics by traveling exclusively faster than light. If they exist, they will be born at light speed and slow down as they gain energy, a complete inversion of the normal rules that govern every other particle we know. More than just cosmic speedsters, a field associated with these particles, a tachyon field permeating all of space, could hold the key to the accelerating universe. The mathematics of such a field produces a unique form of negative pressure, an equation of state that acts as a powerful repulsive force. Picture a cosmic engine that runs on inverted logic, where gaining energy means slowing down. This bizarre property translates into a gravitational effect that pushes the fabric of spacetime apart. As this tachyon field evolves and its energy density changes over cosmic time, it could perfectly mimic the behavior we attribute to dark energy. It offers a specific, albeit speculative, mechanism for the universe's missing energy, one rooted in a fundamental rewrite of particle physics. Imagine a surfer on an infinite ocean, constantly riding just ahead of their own wake. They are propelled not by the wave behind them, but by the strange, inverted physics of the medium itself. A tachyon field would be that medium for the cosmos, a background energy that pushes galaxies apart because its underlying rules are the exact opposite of everything we consider normal. The appeal is its directness, providing a concrete, if unproven, candidate for the dark energy that fills our equations. Yet, the very nature of tachyons makes them notoriously difficult, if not impossible, to detect directly, leaving this elegant idea suspended in the realm of theoretical possibility, a ghostly solution to the greatest ghost in the cosmic machine. The violent birth of our cosmos might not have been a singular event, but the latest chapter in an eternal, repeating story. The ekpyrotic universe theory proposes a breathtaking alternative to the Big Bang, one where our entire reality was forged in the collision of two other worlds. In this model, our three-dimensional universe is a brain, a vast membrane floating in a higher dimensional space, just as we explored before. But here, the story is cyclical. For eons, our brain and a parallel one drift slowly toward one another, drawn together by an invisible force across the bulk. When they finally meet, the impact is not a cataclysm of pure energy, but a transfer of kinetic energy that sets our brain quivering, hot and dense. This collision becomes our Big Bang, a fiery beginning born from a clash of titans in a hidden dimension. This single idea elegantly solves two of cosmology's most stubborn problems. The horizon problem, the puzzle of why the universe is so uniform, is answered by the slow, gentle approach of the brains. Their long, drawn-out dance before the collision naturally smooths out any irregularities, leaving behind the remarkably even cosmic background radiation we observe. The flatness problem, the mystery of the universe's precise geometric balance, is also resolved. Each cosmic cycle acts like a reset button, wiping the slate clean and ensuring the new universe begins with the flat geometry required for long-term stability. But where does dark energy fit into this endless cycle? In this model, the dark energy we measure today is not a permanent feature of the vacuum. It is a temporary phase, a cosmological spring that is slowly winding up. The current epoch of accelerated expansion is not a one-way trip to emptiness, but a necessary preparation for the next great collision. As dark energy drives the universe to expand faster and faster, it also dilutes all matter and radiation to near nothingness, creating a vast, smooth, and empty canvas. This pristine state is the perfect condition for the brains to align, approach, and collide once more, initiating a new Big Bang and a fresh universe. The dark energy density is effectively reset with each new cycle, its value not a mysterious constant, but a consequence of the cyclic mechanics themselves. Our universe's missing energy is not missing at all. It is simply the fuel for its own rebirth, a temporary driver in an infinite cosmic dance of creation, destruction, and renewal that has no beginning and no end. A hidden sector of reality might operate by rules so alien that our very idea of a particle breaks down. This is the speculative world of unparticle physics, a theory proposing a shadow realm that does not consist of protons, electrons, or any other discrete particles we recognize. Instead, this sector is scale invariant, meaning it looks the same no matter how much you zoom in or out. There are no individual building blocks, just a smooth, continuous substance that behaves more like a fluid or a field than a collection of distinct points. Think of it like watching a school of fish from a great distance. You do not see individual fish, but a single, shimmering, flowing shape that moves as one cohesive whole. Unparticles are that shimmering shape, a fundamental aspect of nature that exists without ever breaking down into separate, countable pieces. This strange substance, the theory suggests, interacts only very weakly with the normal matter of the standard model. It simply flows through our world and through us almost completely unnoticed. Yet, despite its ghostly nature, it would still carry energy and exert a gravitational influence on the cosmos. The mathematics of this scale invariant stuff produces a unique form of energy density, one that could perfectly mimic the repulsive push of dark energy. As the universe expands, this unparticle energy density evolves in a specific way, providing the gentle but relentless pressure that drives galaxies apart. It offers a novel solution from beyond the standard model, suggesting that the missing energy is not a property of empty space, but a signature of an entire hidden reality operating just beyond our perception. We have been searching for particles to explain the void, when the true answer might be something far stranger, a seamless, unparticled ocean in which our fragmented world of atoms and stars is merely a fleeting impression. Perhaps the most elegant solutions are the ones we cannot see. A universe of perfect symmetry would demand a partner, a cosmic twin born from the same fundamental laws. Theory 21 proposes that our reality is not alone, but is inextricably linked to a mirror universe, a perfect reflection with one crucial difference: its chirality. Chirality is the property of handedness. Your left and right hands are mirror images, identical in structure yet impossible to superimpose onto one another. They are chiral. In particle physics, this concept applies to the spin and decay of certain particles. Our universe exhibits a curious preference for one hand over the other, a fundamental asymmetry written into the weak nuclear force. This mirror universe would be a copy of our own, with its own galaxies, stars, and perhaps even life, but built from matter that is the mirror image of ours at the most fundamental level. It would coexist with us, separated not by space, but by a different dimension of reality, forever invisible. How could such a hidden twin explain our missing energy? The answer lies in the one force that might be able to bridge the gap between these two realities: gravity. While light and matter are confined to their own universe, gravity, the curvature of space-time, could be a universal force leaking between the two worlds. The gravitational influence of all the matter and energy in the mirror universe could be subtly pulling on our own cosmos. From our perspective, we would feel this extra gravitational tug without being able to see its source, an effect we would misinterpret as a mysterious missing mass, a component of dark matter. But the connection could go deeper than gravity. The two universes might be engaged in a continuous, gentle exchange of energy. If energy were slowly flowing from our universe into the mirror one, the loss would manifest as a deficit in our own cosmic ledger. We would measure a universe that seems to be losing its driving force, an acceleration that appears to require an unknown energy source to sustain it. The energy is not missing, it is simply being shared with our silent twin. This creates a beautifully symmetric solution to our profoundly asymmetric problem. The imbalance we struggle to explain in our universe is perfectly balanced by an equal and opposite condition in the mirror world. We are not an island, but one half of a cosmic whole, and the greatest secret of our existence may be written in the reflection we can never directly observe. The universe may be forgetting, and gravity is the memory of that loss. To understand this, we must look at the cosmos not through the lens of force, but through the laws of thermodynamics. The second law of thermodynamics is one of the most trusted principles in all of science. It states that the total disorder or entropy of an isolated system always increases over time. A cup of hot coffee cools down, its heat dispersing into the room, increasing the overall entropy. Your desk naturally becomes more cluttered, not less. Now, a radical idea suggests that gravity itself is not a fundamental force, but a consequence of this universal tendency toward disorder. This is the entropic force theory. Imagine a simple, everyday miracle. A polymer, like a strand of DNA in a solution, is jostled by water molecules. It starts in a coiled, ordered state. Over time, the random collisions cause it to stretch out into a more disordered, higher entropy configuration. If you were to try to push it back into its tight coil, you would feel a resistance. This resistance is not a fundamental force of nature, it is an entropic force. It emerges purely from the system's statistical drive toward greater disorder. Proponents of this view argue that gravity is the cosmic version of this phenomenon. The force we feel as gravity is the universe's way of maximizing its entropy on the largest possible scale. When a star holds planets in orbit or a galaxy clusters together, it is not because of a fundamental attraction described by Einstein's equations, but because those configurations represent a state of higher entropy for the cosmos. The holographic principle is key here. It suggests that the information describing our three-dimensional universe is actually stored on a two-dimensional surface at its boundary. Gravity, in this view, emerges from the changes in the information or the entropy on that distant cosmic screen. How does this connect to the universe's missing energy? When you apply this thermodynamic logic to an expanding universe, a remarkable term appears in the equations. As the cosmos grows, the amount of information on its boundary increases. This growth in information content, this rising cosmic entropy, naturally produces an effective negative pressure. It is a push that arises from the universe's need to maximize its disorder. This push is mathematically identical to the dark energy driving the accelerated expansion we observe. The energy is not missing from a substance or a field. It is the energetic signature of the universe's increasing forgetfulness, a side effect of the cosmos writing more and more information onto its final boundary. In this breathtaking picture, the force that binds the stars and the energy that tears them apart are two sides of the same coin, both emerging from the deep thermodynamic urge toward chaos. The mystery of dark energy transforms from a hunt for a phantom substance into a calculation of cosmic information, leaving us to wonder if the universe is not just expanding but thinking, and that its thoughts are what push the galaxies ever farther apart. Our cosmic address might be far more special than we ever dared to believe. For decades, cosmology has been guided by the cosmological principle, the grand assumption that on the largest scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every location. It is a statement of cosmic humility, asserting that we do not occupy a privileged place in the cosmos. But what if this foundational principle is wrong? Theory 23 dares to ask this very question. It is known as the void hypothesis, and it proposes that we live inside a giant cosmic underdensity, a vast bubble of relatively empty space, a void. This single idea turns the mystery of dark energy on its head, suggesting the accelerating expansion is not a global property of the universe, but a local illusion created by our unlucky location. Imagine you are standing in the center of a vast, shallow crater on an otherwise flat plain. When you look toward the rim of the crater, the ground appears to slope upward in every direction. You might conclude that you are at the bottom of a giant bowl and that the entire landscape is curved. But if you could teleport to the rim, you would see the truth, a mostly flat plain with one single large depression. The void hypothesis applies this same logic to the entire observable universe. We may be living in the cosmic equivalent of that crater. In a universe that is mostly dense with matter, our local region is an immense billion light-year wide bubble where the density of galaxies is significantly lower than the cosmic average. How does this create the illusion of acceleration? The answer lies in gravity's relentless pull. Regions of space with higher density have stronger gravitational fields, which slows down their local expansion rate. Regions with lower density, like our proposed void, have weaker gravity, allowing them to expand faster relative to the denser surroundings. From our vantage point inside this expanding bubble, we would observe a specific effect. When we look at distant supernova, the standard candles used to measure cosmic expansion, their light has traveled through both the underdense void and the denser universe outside. The observed dimming of that light would not follow the pattern expected for a uniformly expanding universe. Instead, it would look exactly as if the expansion rate is increasing, mimicking the signature of dark energy. We are not measuring a mysterious repulsive force, but simply the gravitational consequences of our position inside a giant cosmic hole. The energy is not missing, our data is merely skewed. This is a profoundly unsettling idea. It means the entire edifice of modern cosmology, built upon the assumption of a uniform universe, could be resting on a statistical fluke. The void hypothesis replaces the mystery of dark energy with a different, equally staggering mystery: the sheer improbability of our existence in such a vast, atypical region of space. Are we the cosmic exception that proves the rule, or is the rule itself a grand and elegant fiction? Empty space itself might be a frictionless ocean. The superfluid vacuum theory proposes that what we perceive as nothing is actually a state of matter known as a superfluid, a quantum liquid that flows eternally without any viscosity or resistance. This is not just an analogy, it is a radical redefinition of the vacuum. On Earth, we can create superfluids by cooling certain liquids like helium to near absolute zero, where they begin to exhibit bizarre quantum behavior on a macroscopic scale, climbing walls and flowing without friction. The theory suggests the entire cosmos is permeated by this same kind of substance, an ultimate superfluid so cold that its temperature is the absolute zero of reality. Within this cosmic superfluid, the particles we know and love, like electrons and quarks, are not fundamental dots but rather excitations, much like ripples or vortices swirling in a fluid. Even gravity could emerge from the dynamics of this medium. The way a vortex in water creates a pull on nearby objects, defects and vibrations in the structure of the superfluid vacuum could generate the force we experience as gravity, all without needing the curved spacetime of general relativity. This leads us directly to the mystery of dark energy. If the vacuum is a superfluid, then its expansion and behavior are governed by the laws of fluid dynamics. The observed acceleration of the universe might not be driven by a mysterious repulsive force, but by the natural pressure and flow of this underlying quantum liquid. Imagine a pot of water slowly coming to a boil. At first, it is calm, but as heat energy increases, bubbles of vapor form and expand, pushing the liquid aside and accelerating their own growth within the medium. In a similar way, the superfluid vacuum could be undergoing a large-scale phase transition or experiencing an internal pressure change as the universe evolves. The galaxies would be like flotsam on this expanding fluid, carried apart not by a ghostly energy, but by the intrinsic dynamics of the medium itself. The energy propelling the cosmos would be an inherent property of the superfluid, a stored potential energy being released as the fluid finds a new equilibrium. This transforms the search for dark energy from a hunt for a missing component into a study of the fundamental state of reality. The answer to our greatest cosmic puzzle may not be found in the void between galaxies, but in the profound and flowing nature of the void itself. The most perfect prisons in the universe might not be so perfect after all. Black holes have long been considered the ultimate in points, regions of spacetime where gravity is so intense that nothing, not even light, can escape their grip. Anything that crosses the boundary, the event horizon, is lost to our universe forever, or so we once thought. This idea, however, creates a profound conflict with one of quantum mechanics' most sacred principles, the law of information conservation. Quantum physics insists that information can never be truly destroyed. If you burn a book, the information in its pages is not gone. It is just chaotically scrambled into the smoke and ashes. In principle, with perfect knowledge, you could reverse the process and reconstruct the book. A black hole seems to violate this fundamental rule. When matter falls in, all the information about its properties, its structure, its very identity, appears to be permanently erased from our reality. This is the black hole information paradox, a screaming contradiction between our two most powerful theories of nature. How could this cosmic censorship possibly connect to the universe's missing energy? The resolution may lie in the black hole's surface, the event horizon itself. Stephen Hawking discovered that black holes are not completely black. Due to quantum effects, they slowly evaporate, emitting a faint glow of radiation. This Hawking radiation carries away energy, causing the black hole to shrink over astronomical timescales until it potentially vanishes entirely. But what happens to all the information that fell in? One leading idea is that the information is not lost inside the singularity. Instead, it is meticulously encoded on the event horizon, a vast two-dimensional hologram storing a perfect record of everything that ever crossed it. As the black hole evaporates via Hawking radiation, this information is not destroyed but slowly and chaotically radiated back out into the universe. Think of the black hole as a cosmic supercomputer that is constantly running, processing the information it consumes, and then broadcasting its results back into space as it evaporates. This process of encoding and re-emission is not free. It requires energy and has gravitational consequences. The energy budget of a black hole is not a simple one-way street. There is a continuous, subtle exchange happening at its boundary. Could it be that the energy we perceive as missing from the large-scale cosmos is somehow tied up in this grand cosmic accounting? The energy that seemingly vanishes behind the event horizon might not be gone forever. It could be temporarily stored as information, a latent energy that is gradually released back into the universe over billions of years through the slow, steady whisper of Hawking radiation. From our distant perspective, trying to measure the total energy of the universe at a single moment in time, this slow, cosmic recycling process could create the illusion of a deficit. We are trying to take a snapshot of a flowing river, and in that instant some of the water is hidden from view, passing through the complex, unseen channels of black hole thermodynamics. The void in our equations might not be emptiness, but a universe busy at work, processing the very information of existence itself in the darkest places imaginable. Our most trusted numbers might be slowly drifting. For centuries, the fundamental constants of nature have been treated as fixed pillars of reality, unchanging numbers like the gravitational constant, big G, or the fine structure constant, which governs the strength of electromagnetism. These values are plugged into every equation, from the orbit of planets to the energy levels of atoms. But what if these pillars are not made of stone but of sand, subtly shifting over billions of years? This is the startling proposition of variable constants, a theory that rewrites the cosmic rulebook. If the strength of gravity itself has been slowly weakening since the Big Bang, the implications for cosmic expansion are profound. The gravitational pull that acts as a brake on the universe's expansion would have been stronger in the past. This means that for the universe to have reached its current size, the initial push from the Big Bang would not need to have been as powerful as our current models suggest. We are trying to understand the cosmos using a fixed value for gravity that may no longer be correct. Imagine driving a car while the friction of the road is constantly, imperceptibly decreasing. You press the accelerator with a certain force, expecting a certain level of resistance, but the car gradually coasts farther and faster than your calculations predicted. You might assume there is a hidden engine helping you, a form of dark energy, but the real explanation is that the friction, the gravitational pull in our cosmic analogy, was not a constant. It was higher at the start of your journey and has been dropping ever since. A varying gravitational constant would naturally alter the expansion history of the universe, potentially creating the observed acceleration without any dark energy at all. The perceived need for a missing component could be an artifact of our stubborn belief in an unchanging world. We are trying to balance the cosmic books using a single, fixed exchange rate for gravity, when the true rate has been fluctuating for eons. The mystery of the universe's missing energy might dissolve into the far grander mystery of a cosmos whose most basic rules are still being written. Even the most stubborn rules of the quantum world can create pressure on a cosmic scale. This brings us to the 27th theory, which looks not to new forces, but to a fundamental quantum law that prevents matter from collapsing in on itself. The Pauli exclusion principle states that no two fermions, the class of particles that includes electrons, protons, and neutrons, can occupy the exact same quantum state at the same time. You can think of it as the ultimate cosmic rule against overcrowding. This principle is the reason atoms have structure and solid matter cannot simply pass through other solid matter. When you sit on a chair, you do not fall through it because the electrons in the atoms of your body are repelled by the electrons in the atoms of the chair, all enforced by Pauli's rule. In extreme environments, this resistance to overcrowding generates a powerful, non-thermal pressure known as degeneracy pressure. It is this very pressure that supports white dwarf stars against the crushing weight of their own gravity, preventing them from collapsing into black holes. The particles inside are squeezed so tightly that they have nowhere to go, and the exclusion principle forces them to push back with immense force. Now, imagine this principle scaled up to fill the entire cosmos. What if the vacuum of space itself were imbued with a kind of degenerate energy field, a cosmic substrate where fermionic fluctuations are packed to their quantum limit? Such a universe-wide degenerate state would naturally exhibit a persistent negative pressure. This is not a mysterious anti-gravity, but a quantum mechanical push born from the simple, unyielding refusal of nature to allow identical states to overlap. In this speculative picture, the accelerated expansion of the universe is not driven by a new form of energy, but by the innate pressure of a quantum vacuum operating under the strict rules of the exclusion principle. The galaxies are being pushed apart by the same fundamental law that keeps the ground firm beneath your feet. It is a profoundly elegant connection, linking the behavior of the largest structures in the cosmos directly to the quantum statistics governing the smallest particles. Could the universe's greatest mystery be solved by one of its most basic and reliable rules? We are living at a very special moment in cosmic history, and this is not a trivial observation. The energy density of dark energy and the energy density of matter in the universe are, right now, almost exactly the same. This is the cosmological coincidence problem, and it is a statistical nightmare. For nearly the entire 14 billion-year history of the cosmos, matter was overwhelmingly dominant. Its density has been relentlessly diluted by expansion, while dark energy's density, if it is a cosmological constant, has remained the same. We just happen to be alive during the brief sliver of time, a cosmic blink of an eye, when these two colossal numbers have become comparable. The odds of this occurring by pure chance are astronomically small. It is as if you walked into a library containing every book ever written, reached for a single random volume, and opened it to the one page that held the secret to your own life. This perfect alignment feels too convenient to be an accident, leading many physicists to suspect a deeper connection is at work. One compelling solution lies in a dynamic form of dark energy known as tracking quintessence. This is not the simple, steady hum of a cosmological constant, but an energy field that is cleverly coupled to the dominant component of the universe throughout its history. In the early, radiation-dominated era, the quintessence field would have mimicked radiation. When matter took over, its energy density would have evolved to track the density of matter. It is a cosmic chameleon, always adjusting its behavior to stay in a specific ratio with whatever is currently in charge. Only recently, as matter's density dropped below a critical threshold, would this tracking field have broken free and begun to behave like the dark energy we observe, its repulsive push finally overcoming the pull of gravity. In this model, the coincidence is not a coincidence at all, but the inevitable outcome of a cleverly designed cosmic mechanism. The energy densities are similar today because the laws of physics were structured to make them so. Another, even more direct, idea proposes that dark energy and dark matter are not independent actors. They could be two sides of the same coin, interacting with each other in a continuous cosmic dance. In this coupled model, energy is slowly leaking from one reservoir to the other. Perhaps dark matter is decaying into dark energy, or maybe dark energy is transferring its properties to the dark matter halo of a galaxy. This creates a feedback loop that naturally keeps their densities locked in a rough balance across billions of years. The missing energy is not lost, it is simply flowing between two accounts we have mistakenly kept separate. We have been trying to balance the books for dark matter and dark energy on individual ledgers, when in reality they are part of a single coupled system with a shared budget. The profound stillness we measure in the vacuum of space might be the calm eye of a storm, the temporary equilibrium point in an eternal exchange between the two greatest unknowns in the universe. The universe may be built upon cosmic scars left over from its fiery youth. Moments after the Big Bang, as the cosmos cooled, the fundamental forces of nature may have undergone sudden, dramatic shifts, much like water freezing into ice. These cosmic phase transitions could have left behind permanent wrinkles in the fabric of space-time, imperfections known as topological defects. These are not mere flaws, but stable, persistent structures like cosmic strings, which are incredibly thin, unimaginably dense lines of energy, or domain walls, vast two-dimensional sheets that partition regions of space with different properties. They are called topological because their stability is guaranteed by the overall geometry of the universe, making them as difficult to erase as a knot in a piece of string. For decades, these defects were studied as potential seeds for the clumping of matter into galaxies, but a new possibility has emerged. Could these ancient relics also be the source of dark energy? The mathematics reveal a startling property. Certain types of these defects, particularly a class known as textures, can exert a persistent negative pressure. This is not a force in the traditional sense, but a consequence of their inherent tension and energy density. They would behave like a strange, cosmic fluid with an equation of state that drives repulsion rather than attraction. Imagine a vast, invisible net embedded within the cosmos, a relic from the first second of existence. This net is under immense tension, constantly trying to shrink and smooth itself out. But because it is woven into the expanding fabric of space-time itself, its attempt to contract actually results in a gentle, relentless push on the universe as a whole. It is like trying to pull on a rope that is tied to an expanding balloon. Your pull inadvertently stretches the balloon even further. This negative pressure, spread uniformly across the vastness of space, could perfectly mimic the effects of a cosmological constant, accelerating the expansion of galaxies without requiring any new, exotic substance. The energy is not missing, it is locked into the very architecture of reality, a fossilized energy from the universe's first moments that is now shaping its ultimate fate. This theory offers a profound elegance, weaving the explanation for dark energy directly into the historical tapestry of the cosmos, suggesting that the answer to our greatest modern mystery was imprinted into existence when time began. Our reality might be the ultimate artifact. The simulation hypothesis pushes speculation to its absolute limit, suggesting that our entire universe, with its billions of galaxies and trillions of stars, is not the base level of existence. Instead, it could be an intricate digital construct, a simulation running on a computer of unimaginable power in a higher reality. If this is true, then the greatest puzzle in physics, the universe's missing energy, transforms into something entirely different. It may not be a physical substance we have failed to detect, but a feature, or perhaps a flaw, in the very code that generates our world. The cosmological constant problem, that staggering mismatch between the predicted and observed vacuum energy, could be a simple resource allocation issue. The creators of the simulation may have dialed the vacuum energy down to nearly zero because that is the most computationally efficient setting. A higher value would require exponentially more processing power to calculate the violent quantum fluctuations of every point in space, potentially slowing the simulation to a crawl or crashing it entirely. The eerie fine-tuning that allows for our existence is no longer a miraculous coincidence, but a necessary parameter set by the programmers to ensure the simulation remains stable and interesting long enough for complex structures like galaxies and life to emerge. Alternatively, the missing energy could be a deliberate glitch. Just as a video game might have a hidden debug mode or unused assets, the vacuum energy we measure might be a placeholder, a variable in the cosmic code that was never fully implemented. We are measuring the equivalent of an empty line in the universe's source code. This reframes our entire scientific quest. We are not physicists discovering fundamental laws. We are reverse engineering the operating system of a reality we did not create. The search for a theory of everything becomes the hunt for the simulation's ultimate programming language. Every strange quantum effect, every paradox of black holes, could be seen as a clever optimization or a rounding error in the computational substrate. The profound silence of the vacuum is not a physical mystery, but the quiet hum of an idling processor, conserving its cycles for the complex task of rendering a cosmos. Is the energy missing, or was it simply never written into the script? From modified gravity to colliding brains and cosmic simulations, the sheer diversity of these 30 theories is a testament to human creativity. We have journeyed from the ghostly push of a cosmological constant to the violent end of a big rip, from the holographic projection of reality to the silent leakage of energy into a mirror universe. Each idea, no matter how strange, represents a profound attempt to answer the same fundamental question. This search for the universe's missing energy is not a sign of failure, but one of the most vibrant and exciting frontiers in all of modern science. It forces us to question our most basic assumptions about space, time, and the very nature of reality. The mystery remains unsolved, a blank canvas waiting for the next great discovery. So we turn the question to you. After this journey through cosmic possibilities, which of these theories resonates most deeply with your own view of the cosmos? Do you believe the answer lies in rewriting gravity in unseen dimensions or in the quantum foam of empty space? Share your favorite theory in the comments below. And if you enjoyed this deep dive into the universe's greatest secret, subscribe for more explorations into the mysteries that shape our reality.